got two pictures on the board here. You're going to recognize both of them. In the first picture, I have object number 1 traveling to the right with a velocity of, let's say, 10 meters per second. Object number 2 is sitting there at rest, so its velocity would be 0 meters per second. Let's say these two objects collide, they stick together, and they head off as one to the right after the collision. What's going to happen to them? Speed up or slow down? You would expect them to slow down, right? If we have the same amount of momentum with more mass, they're going to be going slower. Okay, intuitively, if you have two objects combined, they're not going to be moving as fast as the one object was before the collision, right? How would you analyze this? We've done this several times. We'd say Pi is equal to Pf. We'd say M1 V1I plus M2 V2I equals, if they stick together, M total times Vf. If they don't stick together, then it would be M1 V1F plus M2 V2F. What's V1I? What's V1I here? Just tell me what the number is, quick. 10 meters per second. What's V2I, Jack? 0. So the momentum of this is 0 because its velocity is 0. Does that make sense? Okay, this is not new. So far, this is not new. All right, let's look at another one now. Let's say this time object number 1 is at rest, and object number 2 is coming down towards it like this with a speed of, let's say, 15 meters per second. They stick together. They head off as one. Where are they going to go? Down. How do we analyze this problem? Well, similar way, we just say Pi is equal to Pf. We'd say M1 V1I is equal to, or sorry, plus M2 V2I, because they stick together, is equal to M total times Vf. What's V1I this time? Nope. What's V1I? What is it? 0. Object number 1 is at rest, right? Jack, you were thinking of V2I, and you correctly, I'm glad you caught that, said that it was negative 15 because it was going down. Nope, so the second object is 15 meters per second going down towards the first, but the first object is at rest, 0 meters per second. So it's just sitting there waiting to get hit by the second object. So we're going to say that V1I is 0, V2I is negative 15. Okay? So over here, V1I was 10, V2I was 0. Here, V1I is 0, and V2I is negative 15. Good? In both of those cases, we could solve for Vf, right? Whatever Vf works out to be. We can't actually solve this because we don't have numbers, but we could if we had numbers there. Not crazy, right? You guys can do questions like this. What if you get a question that doesn't look exactly like either of these two? What if you get a question where you have object number 1 moving to the right at 10 meters per second, like you did up here, and you have object number 2 moving downwards like this at 15 meters per second? Where are they going to go when they hit each other now? Say they stick together, head off as one. Where are they going to go? Very good. Down, straight down? No, they're not going to go straight down. There was a downward momentum before the collision. There has to be a downward momentum after, right? But there was also a rightward momentum before the collision, so there has to be a rightward momentum after. So where's it going to go? Not down, not right, but yes, exactly, down and to the right. Where exactly? I don't know exactly where, but somewhere down and to the right. Okay? Now, how do we analyze this? Well, the good news is we pretty much already have. I want to break this up into x components and y components. I'll remind you that this is x and this is y. So break it up into x components and y components. If you do that, if you break it up into x components and y components, watch what happens. The x component ends up being analyzed in exactly the same way as the first problem was up there. Look at this more carefully. If we're analyzing just x, how much of object number 1's 10 meters per second is x? How much of that 10 meters per second is on the horizontal axis? All of it, 10. How much of this 15 is on the x-axis? How much of this 15 is on the x-axis? This is y. Okay, this is the y-axis. How much of that 15 is x? None. So V2I, if we're looking at x component, is 0. It's exactly the same problem as the first one that I put up on the board. Now let's take a look at the y component. If we look at just the y component, then we end up with something that looks like this. It's exactly the same as the second problem that we had up on the board. How much of this, if we're looking at the y-axis, how much of this 10 meters per second right here is on the y-axis? Christian, how much is on the y-axis? None. So we scratch it out. V1I is 0. Like, it's not 0 for the x, but it's 0 for the y. How much of this 15 meters per second is on the y-axis? Negative 15. So we can solve for VF for the x component in the same way as we did if it was a one-dimensional problem. We could solve for VF for the y component in the same way as we did if it was a one-dimensional problem. We get two values of VF. Which one's right? Which one's our answer? The x one or the y one? Well, neither one are right, but we're on the right track. We're well on our way to solving this problem now. What do you think I'm going to do with the VFX component and VFY component? Cindy, what are we going to do here? What are we going to do with the x and the y components here? Exactly. Exactly. We're going to say, here's the x. We're going to say, here's the y, whatever those numbers work out to be. And I'm going to solve for the speed and the angle by doing a little bit of trigonometry. Geometry and trigonometry. V is equal to the square root of a squared plus b squared, and theta is equal to the inverse tan of opposite over adjacent. Is this harder than the one-dimensional problems? Not really. But it's 3 times the work. Right? In the problems that we've been doing thus far, this was a problem where you solved for just one component. And then this was another question. This might have been question number 1. This might have been question number 2. And now we've got a third thing to put into the mix as well, some physics 20 vector analysis. It's 3 questions in one. It's a lot more work than a straightforward one-dimensional problem, but it's not really harder. It's just more work. Let's do example number 1, and then we'll wrap it up from there. 1,200 kilogram car traveling north at 10. Let's draw a picture here since it's two-dimensional. A 1,200 kilogram car, we'll call car number 1, traveling at 10 meters per second, moving north. Then we have another car traveling west at 12 meters per second. Okay, there's car number 2, mass 1,500 kilograms, and the velocity is 12 meters per second. Where do you think this wreckage is going to go? If they stick together, it's going to go. Well, we had a north momentum before, we have to have a north momentum after. A west momentum before, we have to have a west momentum after. It's going to go north and west. Somewhere up here, we think. Now, that is if we're looking at it immediately after, so that we have an isolated system. Now we do our x and our y's. X is pi is equal to pf. Say m1 v1I plus m2 v2I. They stick together, so it's a total mass times VF. Two objects before, two terms, one object after, one term. M1 is 1200. What's V1I for the X component? Remember, this is X, this is Y. How much of that 10 meters per second is X? Somebody just say it out. It goes quicker if you just answer questions. Gareth, how much of that 10 meters per second right here going upwards is X? How much of the 10 meters per second going upwards is X? This is none, right? So I'm actually going to scratch that out. V1I is 0. It's not for the Y component, but it is for the X component. M2 is 1500. That's V2I. Ariel, what's V2I here? How much of that 12 is X? Yes. We're going to make it negative, though, because it's going to the left. Total mass is 2,700 kilograms times VF. 1,500 times negative 12. Divided by 2,700 gives me 6.666. Negative 6.666. Okay, there's the X component. Now let's do the Y's. Say M1 V1I plus M2 V2I equals, once again, M total times VF. What's V1I this time? What's V1I this time? Stephen, what's V1I this time? If we're looking at that 10 meters per second, how much of that is on the y-axis? All of it. Yeah, 10. So we're going to say M1, 1,200 times 10 plus, oh wait, what's V2I? 0. 12 meters per second, but it's all on the x-axis. None's on the y-axis. Equals 2,700 times VF. That's 12,000 on the left side, 12,000. 12,000 divided by 2,700. 4.444. And now we do our little triangle thing. 6.67. 4.444. V is equal to the square root of those, which gives me 8.0 meters per second. Theta is, oh, wait a second. That 4 shouldn't be down, should it? It should be up. It's positive, right? This is negative, it's left. This is positive, so it's up. That doesn't change my numbers there, though. V is still 8 meters per second. Theta is still the inverse tan function of 4.44 over 6.66. It gives me an angle of, gives me 34 degrees. We're going to say that's 34 degrees north of west. Look, this is north, this is west. Where did I measure my angle from? From the west or from the north? What axis is my angle touching, west or north? Look, here's my angle. Is it touching west or is it touching north? Touching west. Okay, so we're measuring it from the west. But yet we're going north from the west. North from west or north of west. And if I had to label my angle right here, then it would be measured from the north, but west from the north. So I would have called that west of north. About 7 minutes left. So take a look at worksheet number 4, question numbers 1 and 2. Worksheet number 4, questions 1 and 2, please.